This presentation is called The Physics of Milling. This is a 75-pound anvil. We attached an accelerometer to the anvil and lightly tapped it with an instrument hammer. The result is the anvil deflected, it rebounded, and then it vibrated back to rest. The takeaway from this is if a 75-pound anvil will deflect and vibrate, so will your milling tool. The milling tool has rotating teeth. Those teeth make an impact on the workpiece with every revolution. And every impact causes the end mill, the tool assembly, to deflect and also rebound. And this is what it looks like. The timing of the tooth impacts is very important. If we arrive too early in that back and forth cycle, we're undercutting the programmed cutting depth. We're leaving a lot of material for the next tooth to have to deal with, and we're throwing off the timing. If we arrive too late, we're overcutting the program depth. That tooth is going to fail sooner than the rest because we're exceeding its chip load limit, and we may be scrapping the part by overcutting the program. Finally, if each tooth is cutting equally, arriving at the same timing and depth, the surface finish is going to be good, the part accuracy is going to be good, and the tool life is maximized. Here's an example of frequencies. There the ruler is stiff, sticking out a short amount. It deflects a small amount, so the back and forth deflection and rebound cycle, or its frequency, is very high. If we stick that same ruler out further, the deflection is greater, so the time it takes to go back and forth in one cycle, rebound and deflect and rebound, it takes longer, and that's a lower frequency. This is how it works with the milling tool. So I've got an end mill and a short, stiff tool holder. The deflection is light, and we can set the timing to get the tooth impacts correctly timed. But we put that same tool holder in a more flexible, the same end mill in a more flexible tool holder. Deflection is greater, and we have to slow the speed down in order to get the timing right. So what makes the tool holder more flexible? Well, it could be length. Some tool holders have to be longer because they have to make room for a collet or some type of mechanism like a hydraulic cylinder or other type of mechanism. It could also be wall thickness. So if a tool holder is using contraction, shrinking, and expanding to hold the tool, the wall is going to have to be thinner to accommodate that, whether through heat or through pressure. So this is the response to a low frequency. We can either slow the speed down to get the timing of the teeth impacts right. We can lower the width of cut or lower the depth of cut, reducing the force on the tool and therefore reducing the amount of deflection. And finally, we can reduce the number of teeth to get the timing right. But each of these solutions reduces the metal removal rate. So low frequency equals lower productivity. Now here's the challenge. The spindle on the machine tool vibrates at one frequency. The tool holder vibrates at another frequency, and then finally we add the end mill, and that vibrates at a third frequency. So the only way to determine what the actual tool point frequency is through a tap test. An accelerometer is placed on one side of the cutter. It's lightly tapped with an instrument hammer. We read the force that's applied and the tool's response to that force. So if you don't measure the tool point frequency, you can only guess at what the proper speed is going to be. So this is what we call the stability lobe diagram. It's only able to be produced through a tap test. Every different tool holder, machine, and material combination produces a different type of stability lobe diagram. A lot of companies use our stability lobe diagrams to promote their product, whether it's a machine tool or tooling. The lower axis of the stability lobe diagram is spindle speed. The left axis is depth of cut. The white areas are stable, combination of speed and depth of cut. The red areas are unstable, where chatter is going to occur. On the far left, or the low speed, you see an area we call the process damped region. This means that the vibration of one tooth is dissipated before the next tooth comes through. So you can cut as deep as you want at these process damped speeds, but they're usually very slow. At a low depth of cut, there's a region called the high-speed machining region. And the depth of cut is shallow enough that it doesn't deflect the tool enough to put it into one of these vibration patterns. And so you can cut as fast as you want. Now, if we were doing tricoidal milling, which is low width of cut or engagement, high depth of cut, we would just flip the depth of cut and width of cut around. So now the left axis is width of cut, and again we have the same tricoidal milling region instead of the high-speed machining region, which is low width of cut. I can run as fast as I want. And this is where most cutters run, in the process damped or the high-speed machining region. Because if you run into chatter, you end up lowering the speed or lowering the depth of cut until it goes away. But if you knew where the deepest, most robust speed was, where this lobe was located, you could have productivity or metal removal rate that's 10 times what you could get at the fastest high-speed machining speed or the deepest process damped depth of cut. So this is an example where we took the same cutter, same end mill, same machine tool, and tested it in 6 different premium tool holder systems. The difference between the best and the worst was 5 times. What that means is your end mill could either perform 5 times better or 5 times worse based solely on the tool holder you chose. Later, we tested the 4 best performing tool holders against the first version of the Smart Tool, and you can see the dramatic difference. We were almost 3 times higher metal removal rate than those other tool holders. And that's where we began with the Smart Tool. So with the Smart Tool, we have a shorter projection, which results in a much higher frequency. Now here's where the problem begins with other tool holder systems. They almost all use just friction to grip the tool. So you have a smooth carbide shank being held in the smooth steel bore of the collet or the tool holder. But carbide is 7 times harder than steel. So there is no way that the tool holder itself is really going to be grabbing into the material of the end mill. It's not going to be deforming it or gripping it like you would see in a lathe chuck on a workpiece. With the spiral flutes of the milling cutter, you have tremendous downward force trying to pull the end mill out of the tool holder. In addition, you've got the forces pressing against each tooth, wanting it to twist inside the tool holder. The result of that is you often see tools pulling out or turning inside the tool holder. It doesn't take much to cause a problem. In this case, a 10,000th difference in stick out, according to Boeing, will change the frequency of that tool. So you need to control the stick out within 10 thousandths. And here, a variation of just 7 degrees, a clocking of 7 degrees of the teeth of the end mill inside the tool holder, tripled the imbalance of the tool assembly. Think of it this way: if you were trying to drive a gear with a motor shaft, you wouldn't just press fit it on and hope that friction would do the job. You would use a keyway and possibly a screw holding it in addition to the keyway on a flat. And that's what we did with the Smart Tool. We have a radius keyway and a screw to hold it in place. The radius of the radius keyway creates forces in multiple directions rather than just a single plane on a regular screw flat. This also allows the tool to be held very accurately and repeatable. Carbide is 7 times harder than steel. It's also 3 times more rigid than steel. So in this case, to match the rigidity of just the straight shank 3/4 inch extended end mill, your tool holder would have to be 2 1/4 inch in diameter. So if you overlay a typical shrink fit holder, you can see they're not coming close to that amount of rigidity. That same thing applies to the steel body of indexable end mills. In most cases, a carbide end mill will outperform the indexable end mill by a large amount, large enough to overcome the price difference of the inserts versus the replacement end mill. We have a very standard product line of short, regular, and long length end mills. You can see that the keyways are located in the same place. The projection is the same. The flute links are the same across all flute types, the 3 flute, 4 flute, 5 flute, 7 flute, and 9 flute. Now we don't have extra long tools, and that's for a reason, because most milling is done on plate stock that is 2 inches thick or less. So those are the tools that we're trying to have in our first product line. But if we don't have a tool that fits the standard in our standard product line, we have an online system that allows you to design a end mill, a complete full special end mill in the Smart Tool Holder, and you can get the price and delivery from Fullerton, but you can also get a dashboard or a stability lobe diagram to show you how that tool is going to work before you buy it, before it's even made. Once you learn how to manipulate the stability lobe diagram, you're going to be able to design tools that are going to perform very well for your customers. For example, in this case, we've extended the capacity of the machine out to 30,000 RPM, even though it's only a 12,000 RPM machine. But this is so we can see where the lobes are going to be located at those higher speeds. The reason for that is we can manipulate or move the dominant lobe, in this case, move it to the left or to a slower speed to fit within the capacity of the machine by lengthening the tool. If we wanted to move it to a faster speed, we can do that by shortening the tool. And also, we can shift the lobes to the right or to a higher speed by increasing the flute count. And finally, if you needed to increase the depth of cut capacity or the amplitude of that dominant lobe, you can add chip breakers to the end mill.